Okay. Um, this lecture is about uh, the compressor with clearance volume. See, here you can see a compressor with clearance volume. See, clearance volume is the volume occupied above the top dead center, in between top dead center and cylinder head. See, it prevents the piston to hit the piston head, and this volume is called clearance volume. So, the effect of clearance volume, see, after the compression and delivery, there will be a small amount of compressed air inside this clearance volume. So, in the next stroke or before the suction stroke, that compressed air expands inside the cylinder. So during this expansion process, we will not get any air, or the compressor will not suck air from the atmosphere. So this expansion process is an effect of clearance volume. And see, at this point A, the suction valve close. At point B, the discharge valve will open. At C, the discharge valve will close, and at G, the suction valve opens. So from C to G, the suction valve remains closed, so we will not get any air. Then this process is an expansion process. It may be same as the compression process, that is a polytropic, or it may be a adiabatic process. Isothermal process is not possible in compression. So it would be either polytropic or adiabatic process. First of all, we are assumed that both the compression and expansion takes place polytropically. The equation for both compression and expansion is PV raised to N is a constant. So the work done by the compressor per cycle, that is the work done per cycle, this cycle is equal to work done during compression minus work done during expansion. So that is area 12341, that is this area enclosed by the cycle, which is equal to area 12651, which is the area under the compression, and area 36543, that is area under expansion. So this is the work done by the compressor per cycle. So these units are very important. See, this unit will be, the unit of work will be joules per cycle. Okay. So substitute polytropic work done for compression and expansion, we will get work is equal to N by N minus 1, where N is the polytropic index, P1 V1 into P2 by P1 raised to N minus 1 by N minus 1 minus n by n minus 1 P4 V4 into P3 by P4 raised to n minus 1 by n minus 1. So these are the work done during compression process and expansion process. Both are polytropic. So we can directly, we have already derived these equations or these expressions. So we can directly substitute these values, terms. Now see, at the point 1 and 4 both are constant pressure process. So P1 is equal to P4. Similarly, P2 is equal to P3, and V3 is nothing but this point is Vc, that is clearance volume. Okay. So substitute P4 is equal to P1 and P3 is equal to P2, then the only difference is V1 and V4. So all other terms are common in two expressions. So we can take it as common. So work is equal to n by n minus 1 into P1 into P2 by P1 raised to n minus 1 by n minus 1 into V1 minus V4. So what is V1 minus V4? See, V1 is this and V4 is this. V1 minus V4 is called effective swept volume. Effective swept volume. That is, actually swept volume is from clearance volume from V3. V1 minus Vc will be the swept volume, but due to the expansion of compressed air inside the cylinder, we cannot use this much volume of cylinder to suck air. So the effective swept volume will be V1 minus V4. So this is called effective swept volume VA. So W is equal to n by n minus 1 P1 into VA into P2 by P1 n minus 1 by n minus 1. Okay. So this is the equation for work done per cycle in a reciprocating compressor with clearance volume. Another important thing is free air delivered. Okay. So the definition of free air delivered or FAD is the amount of compressed air delivered at the outlet of a compressor converted back to the actual inlet conditions before it was compressed. Or in other words, it is the amount of free air drawn in at atmospheric conditions by the compressor, compressed and delivered at a specific pressure. This term is used to compare the performance of reciprocating compressors at different conditions. See, sometimes the atmospheric conditions will not be the same for all the place where a particular compressor is installed. So in order to compare the performance of the compressor, we need a standard. So that standard is free air delivered, and the volumetric efficiency in terms of free air delivered. This is the standard for comparing the reciprocating compressor. See, according to the ideal gas law equation, P1 V1 by T1 is equal to P2 V2 by T2, and this P0 V0 by T0 is the ambient condition of that particular reciprocating compressor, and this V0 is called free air delivered. Now we know that at V1 the volume will be the effective volume, that is V1 minus V4, and at point 2 the effective volume will be V2 minus V3. So P1 into V1 minus V4 divided by T1 is equal to P2 into V2 minus V3 divided by T2, which is equal to P0 V0 by T0. These 0 subscripts are for atmospheric conditions. Next is volumetric efficiency. See, the definition of volumetric efficiency is the ratio of effective swept volume divided by swept volume of the cylinder or compressor. Now, what is the effective swept volume? We already discussed. Effective swept volume is equal to V1 minus V4, and swept volume is Vs, simply Vs. So substitute effective swept volume as Vs minus V4 minus Vc, that is, what is effective swept volume? Effective swept volume is from V1 minus V4, right? So which is equal to, this is a swept volume minus this volume, that is V4 plus Vc. So that is Vs minus, within bracket, V4 minus Vc divided by Vs. Vs is the swept volume, and we are taking this Vc out, then we will get Vs minus Vc into V4 by Vc minus 1 divided by Vs. That is, and if you multiply with Vs, this becomes 1, so 1 minus Vc by Vs into V4 by Vc minus 1. Okay. Now see, instead of V4 and Vc, we can take, or we can rewrite this V4 by Vc in terms of pressures. For that, see, we know that this compression and expansion are polytropic, so we can write V3 raised to n is equal to P4 V4 raised to n. So at this point, 3 to 4, the process 3 to 4 is a polytropic process. So at the point 3, P3 V3 raised to n is equal to, and at the point 4, P4 V4 raised to n, which is equal to P3 V3 raised to n. So from that we will get V4 by V3 is equal to P3 by P4 raised to 1 by n. Right? So what is V4? V4 is sorry, what is V3? V3 is nothing but Vc. Okay, and what is P4? P4 is same as P1 and P3 is same as P2. So we can rewrite V4 by Vc is equal to P2 by P1 raised to 1 by n. So substitute V4 by Vc in terms of pressures. So we will get this expression. Volumetric efficiency is equal to 1 minus Vc by Vs into P2 by P1 raised to 1 by n minus 1. Now this term Vc by Vs, which is clearance volume by swept volume, which is called clearance ratio C. So we can rewrite this 1 minus C into P2 by P1 raised to 1 by n minus 1. Or if you multiply this into the bracket, 1 plus C minus C into P2 by P1 raised to 1 by n. So this is the volumetric efficiency of a reciprocating compressor with clearance volume. Okay. Now what is the effect of free air delivery in this volumetric efficiency, or the volumetric efficiency in terms of free air delivery is the standard for comparing the compressors. So in next slide we will look into it. So we can write the volumetric efficiency in terms of free air delivered, which is volume of free air taken per cycle divided by swept volume of the cylinder. So instead of V1 minus V4, that is effective swept volume, now we take the free air delivered. And we know that the free air delivered V0 in terms of P1 and V1 is equal to P0 by T0 into P1 by T1 into V1 minus V4. So this is the free air delivered. So substitute this value in volumetric efficiency, you will get this expression. Okay. So in terms of free air delivered, the efficiency volumetric efficiency is equal to this. See, this term is nothing but the volumetric efficiency if you are not considering the free air delivered. Okay. Now sometimes they may ask the free air delivered will be at the atmospheric conditions. So which means, or the suction conditions are atmospheric condition, then P0 will be equal to okay. This expression was wrong previously. Okay, right now it's okay. Suppose the suction conditions are the same condition of the atmosphere, then T0 will be equal to T1 and P1 will be equal to P0. So this term cancels. We will get V1 minus V4 by Vs, which is equal to normal volumetric efficiency. Now we will do some problems. This is a university question. A single stage single acting reciprocating compressor compresses 7 into 10 raised to minus 3 meter cube of air per second from 1.032 bar to 14 bar. The index of polytropic compression is 1.3 and mechanical efficiency 82%. If the clearance is 3% of sept volume, determine the volumetric efficiency and power required to drive the compressor and show the process on a PV diagram. So this is the question. Now the given data, this is effective volume, that is at V1 7 into 10 raised to minus 3 meter cube per second. Note that the unit is meter cube per second, not in meter cube per cycle. Okay. Now P1 is equal to 1.0132 bar and P2 is equal to 14 bar. See, these units are in bar. You have to convert it into Newton per meter square while doing the problem. N is equal to 1.3 and mechanical efficiency 82%. This is clearance volume is given as 0.03 of sept volume. Now from this we can calculate clearance ratio Vc by Vs is equal to 0.03. Now volumetric efficiency, this is the expression for volumetric efficiency, 1 plus C minus C into P2 by P1 by 1 raised to 1 by N. So substitute all the values are given. So substitute all the values, you will get 80.386% volumetric efficiency. Now power supplied to the compressor. See, we know that this compressor is a power consuming machine. We have to give some power to compress the air. So that power supplied to the compressor, if we are assuming that there is no losses, it will be equal to the work done per second. So work done per second is the power, so which is equal to N by N minus 1 P1 into VA into P2 by P1 N minus 1 by N minus 1 itself, because here the volume VA or V1 is in meter cube per second. Sometimes it may be in meter cube per cycle. If it is in meter cube per cycle, you have to convert it into meter cube per second. For that, multiply this expression with N by 60, where N is the speed of the compressor, revolutions per minute RPM, by 60. From that we will get power is equal to 2.5525 kilowatt. Okay. Now see, in actual case the actual power supplied to the compressor will be more than this due to mechanical losses. That is what we call mechanical efficiency, right? If there is no losses, then mechanical efficiency will be 1. So mechanical efficiency is equal to work done per second divided by actual power supplied. So that is equal to 82%. So work done per second is 2.5525 and we have 82% efficiency, then actual power supplied is equal to approximately 3.113 kilowatts. And you have to draw a PV diagram like this and mark all the points, salient points in the diagram. And sometimes they may ask the V1, V2, V3 and V4 etc. Then you can easily calculate, for example, you have to calculate V2, the volume at point 2. What will be the volume at point 2? We can apply the polytropic equation, that is PV raised to n. P1 V1 raised to 1.3 is equal to P2 V2 raised to 1.3. So P1 is given, P2 is given and V1 is also given. The only unknown is V2. We can find. Similarly, we can find V4. How? See, 3 to 4 is a polytropic process. Then P3 V3 raised to 1.3 is equal to P4 V4 raised to 1.3. P3 is equal to P2 and P4 is equal to P1. The only unknown will be, or the V3 is nothing but clearance volume. V3 is equal to Vc, right? And swept volume, if you have the stroke and bore, you can calculate the swept volume. Swept volume is pi by 4 d square into L. D is the bore diameter, L is the stroke length. So you can calculate swept volume. And all the pressure and volume values can be calculated once you get the P1 V1 and P2 V2. Now the second question. This is second question is also a university question. A single acting reciprocating air compressor with air entering at 1 bar and leaving at 7 bar following PV raised to 1.3 is equal to a constant. Free air delivered is 5.6 meter cube per minute and mean piston speed is 150 meter per minute. Take stroke to bore ratio of 1.3 and clearance volume to be 1/5 of the swept volume per stroke. The suction temperature and pressure are atmospheric. Determine the volumetric efficiency, speed of rotation and stroke and bore. See, the first thing you have to note is this suction temperature and pressure are atmospheric. That means at the suction condition V1, that is V1 minus V4 is equal to free air delivered, right? I told you in the volumetric efficiency topic, that is the condition for suction condition same as the atmospheric condition. So this is such case. Okay. Now the given data is P1 1 bar, T1 27 degrees Celsius converting to Kelvin, P2 7 bar, N is equal to 1.3, VO, that is free air delivered 5.6 meter cube per minute, convert it into meter cube per second. Piston speed, see, this is also important. See, piston speed is given as 150 meter per minute. Piston speed. So that is, in one rotation of crank, the piston moves or piston completes two movements, one upward or forward movement, one backward movement. So the piston speed in n revolutions will be 2L, right? So 2L into n is the piston speed, which is equal to 150 meter per minute. Now if you convert this into seconds, then it will be 2.5 meter per second. And stroke length L is equal to 1.3D, that is stroke to bore ratio is 1.3 is given. And clearance volume is equal to 1/5 of swept volume. So Vc by Vs, or clearance ratio, is 1/5 or 0.2. Now we are assuming that P0, that is atmospheric condition, is 1.0132 bar. T0 is atmospheric temperature, which is 15 degrees Celsius or 288 Kelvin. Then volumetric efficiency is equal to this: 1 plus C minus C into P2 by P1 raised to 1 by n. So it is 30.65%. Now we can calculate now volumetric efficiency in terms of free air delivered, because we have given free air delivered, is equal to V0 by Vs. So Vs is equal to V0 divided by volumetric efficiency. So that is 0.3034 meter cube per second. Also, we know that swept volume is equal to pi by 4 d square into L, that is the volume of the cylinder, swept volume of the cylinder per cycle. Swept volume of the cylinder, and this is in meter cube, but our volumes are in meter cube per second. So in order to convert it into meter cube per second, you multiply with n by 60. So swept volume is equal to pi by 4 d square L into n by 60, and the velocity of piston velocity is equal to 2ln by 60, and L is equal to 1.3 d. So 3 equations, 3 unknowns. So we can solve n, d and L. Okay. The answer of D, when I solving this, I got it's approximately 0.55 meter. That is, I think it's not possible for a compressor having a 55 centimeter diameter piston. So maybe the question would be wrong. Okay. If you get a correct answer, please comment it in our classroom, Google Classroom. Thank you.